What if the next major blackout isn't caused by a storm, or by equipment failure, but by a single line of code? Today, high voltage direct current, or HVDC, systems are among the most critical infrastructures on Earth. They connect countries, markets, and entire regions, and yet they are becoming increasingly exposed to cyber threats. In this episode, we're going deep into a crucial question. How can we use artificial intelligence to defend these vital HVDC systems against cyber attacks without compromising safety? This is episode 4 of our series on HVDC and cybersecurity. HVDC systems are no longer just isolated electrical assets. They've evolved into complex cyber-physical systems. They rely on digital control platforms, high-speed communication networks, SCADA and EMS systems, and a host of intelligent electronic devices. Traditionally, cybersecurity in the power grid depended on firewalls, static access rules, and signature-based intrusion detection. But here's the problem. Modern cyber threats evolve much faster than these static defenses. The attacks we face now are adaptive, slow-moving, and deliberately designed to look like legitimate operations. By the time a traditional, rule-based system detects them, the damage may already be done. This is why AI is no longer just an option. It's a necessity. AI introduces something that traditional security has always lacked: the ability to learn what normal behavior looks like and instantly detect what doesn't belong. Now, one of the most important architectural questions we have to answer is, where exactly should we place AI inside an HVDC system? There are really two main options. Option 1 is to put the AI inside the control layer itself. In this approach, AI would become a direct part of the control loops, the power balancing logic, and the voltage and current supervision. The advantages seem tempting: incredibly fast reaction times, direct access to all measurements, and a strong correlation between cyber and physical behavior. But the risks are enormous. If an AI inside the control layer is compromised, power flow could be manipulated, grid stability could be affected, and safety margins could collapse in an instant. Certifying such a system would be extremely difficult, and trust would become fragile. That's why this approach remains mostly experimental for now. This brings us to option 2, AI as a dedicated, separate cybersecurity layer. This is the approach used in modern, realistic HVDC architectures. Here, the AI is kept separate from the control systems. It has read-only access, acting as an observer. It doesn't control the system, it watches the system. It analyzes signals, communication traffic, timing, and behavior. Then it reports anomalies, risk levels, and suspicious patterns to human operators. This separation is absolutely critical. It ensures that safety remains deterministic and reliable, while security becomes intelligent and adaptive. At the very heart of this AI-based cyber defense is a powerful concept: the digital twin. A digital twin isn't just a simple simulation. It's a living, real-time mirror of the physical HVDC system. It includes the electrical dynamics, the control logic, the communication behavior, and all the expected operating states. Now, here's the key idea. Cyber attacks often respect communication protocols, but they violate the laws of physics. For example, a false data injection attack might follow all the correct IEC 61850 rules, use valid packets, and look completely legitimate to a traditional system, but it creates a physical inconsistency. The digital twin predicts what should be happening in the real world. The AI then compares the real measurements from the physical system against the digital twin's predictions. If the gap between reality and expectation grows beyond a set tolerance, the AI knows something is wrong. This method allows us to detect sophisticated attacks like false data injection, replay attacks, and coordinated cyber-physical attacks long before operators might even notice a problem. At this point, we need to make a critical clarification. The IEC 622351 standard is essential for cybersecurity, but it's not enough on its own. IEC 62351 focuses on things like encryption, authentication, data integrity, and role-based access control. It's designed to protect the communication channels. It locks the door, but it doesn't answer the question. What if someone with valid credentials, a key to the door, acts maliciously? IEC 62351 can't detect insider threats, compromised but authorized devices, or attacks that slowly evolve over time. This is where AI steps in. AI analyzes command sequences, timing irregularities, statistical deviations, and cross-layer behavior. Together, IEC 62351 and AI form a powerful, layered defense. IEC 62351 secures the door, and AI watches what happens inside the room. A critical design principle must always be respected in this architecture. AI must never directly control the HVDC assets. Instead, AI acts as an advanced cyber sensor. It integrates with existing SCADA and EMS systems by reading logs, monitoring traffic mirrors, and analyzing data from PMUs and the HVDC measurements themselves. Its outputs are things like risk dashboards, confidence indicators, and early warnings. The final decision always remains with trained human operators, engineers, and established emergency procedures. AI assists, but humans decide. So a truly secure, AI-enabled HVDC system includes 5 distinct layers. First, the physical layer with the converters, breakers, and sensors. Second, the control layer, which uses classical, deterministic control for safety. Third, the communication layer, secured with standards like IEC 62351. Fourth, the AI cyber layer, providing behavioral intelligence. And finally, the fifth and most important layer, the human layer, made up of trained operators and strong governance. Each layer protects the others. There is no single point of failure and no blind trust in automation. To be clear, AI will not replace HVDC control systems, and it shouldn't. But without AI, modern HVDC systems will always be one step behind sophisticated cyber attackers. The future of power system security isn't just reactive. It's predictive, it's behavioral, and it's fundamentally human-centered. In our next episode, we'll step back from the technology and ask an even bigger question. Can HVDC supergrids survive a cyber war? Thanks for watching. Stay safe and stay curious.